So let's talk about NFTs and duck typing. But first, let's start with duck typing. What is duck typing? So there is a Wikipedia definition which says if something walks like a duck and if it quacks like a duck, then it must be a duck. So if we do something in the code and where the behavior is more important than some semantic structure, like implementing something, then that's the duck typing, that it's enough to mimic some behavior to be part of an interface group. So what does it mean for the NFT? It's a very well-known fact that most of the NFTs are nothing more just committed links to the blockchain. So, for example, I can choose any of the NFTs here in a NFT marketplace, and I can just click to a random one. And usually I can find the contract address and the token ID. So I copy paste this one and click to here. And here under the contract, I can read the information. So I can call the contract on the blockchain to get the information. And the most important may be this one, the token URI. So if I paste the token ID, I can get a descriptor. Sometimes it's an IPFS, but it can be any URL. So let's check what's going on here. So if I check this one, okay, so this seems to be a descriptor with some kind of attributes, a description, and here we have the image, which is supposed to be the real high-resolution image. So actually this is the descriptor, which is the link to this descriptor is committed to the blockchain, and I have the link which may or may not be available. Usually it should be available somewhere in the internet. So yes, I can check it, and this is the content of the NFT. But what does it mean exactly when I call this token URI? What happens? So what is the interface? Well, I can call exactly the same from console. So I have a simple CLI application which can do any Ethereum call. So all what I need is the target address, the contract. And after that, I can call any method. It doesn't matter if it exists or not. But if I call the token URI with the right parameters, so this is a uint 256, then I can get exactly the same results. So this is the encoding version, but I can also define that please decode the results as a string. And I can see exactly the same results. So if I do a debug, it's also visible that this is the call which is sent to the blockchain. So this is the contract address, this is my generated address, and this is the data which is sent to. And here, the first 4 bytes are the important, because it's bytecode. So actually it's not a duck typing, because we have no interfaces on bytecode, but something happens. But it's the easiest way to understand what's going on bytecode level, I think, just checking this example. So this is part of the Solidity. Solidity also has a support to do some kind of assembly-based programming. And here what we can see is just most of the commands are plain Ethereum VM assembly instructions. And this is a very typical Ethereum contract. Well, it's not an NFT, it's just a token, but the main structure is exactly the same. So what we see here, this is the code part, which is executed when we deploy the contract to the Ethereum chain. And the main part of this contract is nothing more just copy the data from this message. So we are sending one message to the blockchain, similar to this one, and the first code is the deployer code, the few lines, and the other one is just the code of the contract itself. So this persists the runtime code, and this is the runtime code. And first of all, it checks if there is any value, real Ethereum, in this transaction. It should be 0. And after that, there is this switch. So actually, this is the implementation of the interface, because here we can check if somebody called with the 4 bytes with balance off or total supply. So in NFT, there should be a similar case for token URI. And in that case, that's an NFT. It doesn't really matter how is it implemented or which language was the origin source. And we can check this one. So for example, this is a hash actually of this signature, and there is a database for this one. So I can just put any hash and it can print out. Because this is a hash, it's possible to get more than one function signature, but this hash, it matches the balance address. Actually, if I would call the same this method, that would use exactly the same switch case, because the hash of these methods are exactly the same. So this is the NFT definition. So we can just calculate all of the hashes of this one, and if we response or we say quack for all of these 4 bytes hashes of the required methods, then we did an NFTs. Nothing more is required. Again, it's not a real duck typing, right? Because this is a code. But there is a very interesting question that how can I filter all of the NFTs? Well, there is one other option that there is a standard which may or may not be implemented, where there is a 4 bytes method signature to get the supported signatures. And if it's supported, then we can get and we can hope that it's implemented well. But if there is if this ERC-165 is not implemented, the only thing what we can do to understand if one contract implements the NFT or not is checking the code and trying it out if it quacks when we get the token URI. Well, the code may or may not be uploaded to the Etherscan. That's totally optional. So if it's not uploaded, we have no other option, just executing the code itself with some Ethereum, so this code, and check if it handles the 4 bytes, which makes very tricky to get all of the NFTs for any of the chains, because we need to execute it in all of the existing contracts code. But that can be the question of a next video in the future.